Hello and welcome to Toddcast number 28. We're continuing on stereochemistry, specifically enantiomers and diastereomers, and the optical rotation that we observe associated with them, and introducing a couple of terms that will show up more in biology than they do in chemistry, but really want to emphasize that as far as organic chemistry goes, it has enough of a biology component because a lot of the applications we have, interesting synthesis, and the work we get as organic chemists comes from natural products, figuring out how to isolate, purify, identify, synthesize, whatever we may do, compounds that animals and plants make in nature. We're trying to figure out ways to analyze them, purify them, maximize them, synthesize them, whatever we may do. So there is a huge component. So whereas your first inkling, kind of a honestly first year college student, more of a freshman line of thinking is, oh, these are tangents. Reality is, as you learn more and more in science, tangents become interesting examples and careers. So when you think about it, a lot of you want to go into medicine. Medicine is nothing more than a tangent of organic chemistry. So if I'm talking about something, oh, he's going off on a tangent. No, talking about something that's applicable down the road. So you need to change the maturity of your perspective of what these are. So these are applications that transfer from one field to another. There are unique ways of looking at material from an organic perspective that can be helpful in other courses such as biology, physics, general chemistry, different classes you run into. So with that note, want to just introduce that we have very, very similar terms in biochem and ochem, but we use different designations. So you still, for biological molecules, we still have R and S to consider, but for whatever reason, um, they define theirs a little bit differently and use D and L, capital D, capital L. There is no correlation whatsoever between capital D and small d, capital L and small l. So just want to emphasize that. So want to reestablish the L concept, the small letter that we have from chemistry, and then just talk about how these things came into place. So it all started, Emil Fischer wanted to somehow, some way correlate optical rotation to R and S, and in doing so, designated capital D that he assumed to be R, and capital L that he assumed to be S as far as designation to the D and L. It worked great for the very first molecule he looked at, glyceraldehyde. So the unfortunate thing, and this often happens when we make rules based on an n equals 1, if your survey size is 1 and you make all your rules based on it, you sure as heck better hope that's not an exception, or that conversely, you better hope that it's the norm the majority of the time. So that said, it ended up not being that. So he spent this time setting up rules that actually can be counterproductive. But a few things we need to remember. If it's positive, it's dextrorotatory, so we assign it a D. And then the other enantiomer is always the opposite optical rotation. One rotates it clockwise, the other one rotates it counterclockwise. So if it's positive 8.7 for the D, then it's negative 8.7 for the L. Capital D, again, represents the wavelength of light that we're using. Okay, so this is the background information, this fundamental chemistry information that we're going to use for our biomolecules. So he started with glyceraldehyde. So if you're aware, glycerol is this compound. And glycerol, for again, those of you with some bio inkling, is the molecule that picks up a phosphate and two fatty acids to make this phospholipid bilayer of the cell membrane. It also can pick up like a nitrogen species with a charge, carboxylic acid, or carboxylate group, some other group in addition. And in doing so, also add two fats. And so it can be a different thing like a sphingolipid or different sort of application. But it's the background or backbone of that. What glyceraldehyde is you take one of the ols, you're going to choose the one at the end, and you now make it an aldehyde. So no longer an alcohol, we call it glyceraldehyde. Okay, so same compound, so that's what this is. This is, if this was an OH, OH, and OH, it'd be glycerol, instead it's an aldehyde. Okay, so get rid of all this and move along. So this first carbon has H, H, and OH, so two identical groups, not chiral. This end one is sp2, so not chiral. So the only one that can be chiral is going to be this center one. So that star right there, it has CH2OH, acetyl on OH, and OH, and then also has its other group, an H. I don't know if H is coming in or going out because I don't know which of the enantiomers it is. So there's my chiral center. If the OH is in front, that would mean the H would have to be in the back. And so that would be this structure. Or if the OH is in, that didn't come out quite as I'd hoped, but if the OH was in back, so I apologize for that. So that if that is in front, and then if the OH is in back, I'm going to try to do it in a fancy, fun way. That's close enough. So H in back, and I would have this structure right there. Okay, so far so good. And then if I want to draw it just generically, it's back to being the straight line. Okay, so we have this enantiomer and this enantiomer. Just for reference, this chirality is priority 1, H and back, so 2, 3. So this would be an R center. This other one then would be an S. 1, 2, 3, but H in front, so I would reverse it. But it would also be, as it were, this would also be D, this would be L for the Fisher nomenclature. And then it also ends up just, just for what it's worth, that was also the D. That was also the L. That's why he went with the survey one to make this whole correlation, which is what leads to our misconception that there is a correlation. And because his data set was one, it was not enough molecules to make it worthwhile to apply to everything. Okay. So draw the Fisher projection of enantiomers. So here is this one. And so keep in mind your eyebrows up here. So the aldehyde's going to be on top. This be on the right, this be on the left. So OH on the right, check. OH on the left. Aldehyde up top. CH2OH on bottom. Works out well. And then it is D. And it is plus. And I'm going to give you a mnemonic that works almost all the time. You're either a doctor or you lose. Terrible, rude, horrible mnemonic, works really, really well. Very, very few exceptions. I'm going to talk about a couple of exceptions, but generally that holds true. So the same rules we do to get absolute configuration in OChem, the biochemists of the world, like Emil Fischer, took those same things and applied it and just gave the letters D and L, but they don't prioritize quite the same way we do. They prioritize by functional group, not by atoms. And it usually works out, but every now and then there's an exception. Okay. So the other enantiomer, OH in front and H in back here, this one, OH in back, H in front. Looking down on it, the OH is now going to be on the opposite side. So it'll be on the left, the Fisher projection, and it'll make it L. It is also negative. So you're a doctor or you lose. So let me toss it in there. L typically goes with S. D typically goes with R. Not always, but about 99% of the time in bio. Uppercase are not the same as lowercase. Just have to know that. Uppercase are configurations like R and S. Lowercase are absolute rotation, plus or minus rotation. So typically D goes with R, L goes with S, 99% rule. And then D goes with plus, and L goes with minus for rotation. That's your correlation. Okay, so here's my same thing here. I draw this as CHO instead of drawing the aldehyde out the whole way. When it undergoes, so what he found was that when he treated glyceraldehyde and you reduce carbon 3 and you oxidize up carbon 1, so this is a natural process, assuming yeast driven, but I don't know, you get something called lactic acid. So you have glyceraldehyde, you reduce, get rid of the O here, oxidize up here, and you end up, so you have a reduction oxidation process, two separate steps, end up with D-lactic acid. But this is where things got messed up. This is where he realized he kind of screwed things up. And so instead of D plus lactic acid, it's actually D minus lactic acid. So cross it out, not because it's wrong, but because it's not specific enough. So D was positive with one, but D was suddenly negative with the other. So that meant there was no correlation between rotation of light and the letters. He had hoped by calling these D and L that he could combine R being plus and S being minus and make it all work out, and it didn't work out. So we have the different rules. OChem, we use R and S. Bio and biochem, we use D and L. They are the same thing. Sans, the rules are slightly different. We are O-chemists, so I'm only going to focus on the rules for R and S. And then plus and minus, small d, small l. We will typically use plus and minus in OChem. Small d and small l are perfectly viable for bio. Because we use biomolecules in OChem, you have to speak both terms. Okay, so common applications, because Fisher came up with it, the Fisher projections are really common for these. So for designating D and L, you have 1, 2, 3 chiral centers. So Fisher said, go for the penultimate carbon or the last chiral center. Okay, so let me figure out what the chirality is. Remember, these are bow ties. H is coming out, so I'm going to take the opposite. So priority 1 is the O, 2 is the side that goes to the carbonyl, 3 is down here. So counterclockwise, because H is in front, this is R. You're either a doctor or you lose. Mannose, the same designation. And the same priority, 1, 2, 3. But it gets reversed to R. And aniline, so again, these are here. So priority 1, I would say, is N. Priority 2 is carbon with lots of O's. Priority 3, because H in front, it's an S. You're either doctor or you lose. So they call that D-ribose, D-mannose, L-alanine. I do these examples because naturally occurring sugars that we biologically digest and process are almost always D sugars. We digest D. We do have a few random exceptions, like markers on our blood cells sometimes will be L sugars, but very rarely, like blood type markers have a rare case where there's an L sugar involved. But we have D-ribose, D-mannose, D-glucose, D-fructose. Those are the monosaccharides that are common in our body. So D corresponds to R at the last chiral center. Naturally occurring amino acids, for whatever reason, are L. It's one of those cool little fun facts of life. Okay. So natural amino acids. Amino acids are naturally L. They are natural. So we digest sugars. So D for digest. And natural L amino acids. So amino acids are natural. So this would be what's known as a zwitterion. It has charges on the amino terminal positive and carboxyl terminal negative, but overall it's a neutral species. But that's how amino acids exist in biological systems. Aqueous at pH of 1. H is in front, so it is, because of that, an S equals L. Either a doctor or you lose, 99% of the time. Okay, here is our notable exception. This amino acid valine, It's perfectly fine. This amino acid alanine, we just did it, it's fine. Serine is fine. But here is the where things get jacked up between OChem and biochem, and why I want you to know the OChem rules for this class. Priority number 1 is, if I go through these, priority number 1 on this N carbon is N, priority 4 is H, but where things differ is sulfur, the first atom attached to carbon, beats oxygen. So in OChem, my priorities are 1, 2 for this side group, 3 for the carboxyl in there, and 4 for the H. So that would be an R center, but it has the same orientation where they have carboxyl to the right and to the left. So left and right, functional group coming out, H going back. So they call that L in biochemistry and R. So D goes with R, L, or D goes with R, your doctor, or L goes with S, loser, except for cysteine. Cysteine is our exception. So again, it's a 99% of the time rule. Just want to make sure I do an exception to the rule. And just a little bit of bio knowledge. Okay, really cool spot where OChem saves bio. So bio people, they have their pure isomers from plant, but if they try to synthesize them, you don't get pure. So we have to figure out how to isolate it. So let's say you had 2 structures here. They're both alanine. And I want to figure out which alanine is which. So I'm going to do my chirality test. I'm going to start with H and back because that's easiest. So priority 1, 2, 3. So this is R. So this would be D-alanine because it has an R stereocenter. Make the other one L-alanine because it has an S stereocenter. Amino acids are naturally occurring. So an L amino acid, an L enzyme, is going to acylase anything in an ACE is an enzyme. It's going to react the L and not the D. So if I can take this mixture I make naturally, or isolate naturally, or synthesize, or this mixture, I should say, I don't know how I got it, and I take a naturally selecting molecule. So I mentioned it's really hard to physically separate 2 enantiomers. You can't boil them, can't crystallize them because they crystallize together as a paste. They boil at the same temperature, really hard to purify. But enzymes, if I take D and L, my body will select one over the other. So it will only react with the L because that's the only one that fits, has right orientation in its active site. So it will selectively add this group to the acyl. So I mentioned earlier that in the body, things exist as a zwitterion. So negative and positive means overall neutral. Nothing here, and a negative means this is overall an anion. If you put a charge near this, a positive or a negative charge, negative will repel this away, positive will pull it towards it. Negative and positive won't affect this because it's neutral, which means you can separate by affinity chromatography or electrophoresis, things you'll learn in biochemistry, where electrophoresis is putting an electric field. One will move an electric field, one won't. Affinity column is making column of positives or negatives. This one will move through it like nothing happened. This will either move through it faster if it's the same charge or slower. So you can get it to go through a charge column or electric field at different rates and separate them. So now this one is separated from this. If I want to get this one, I just add the same enzyme. So if I add the enzyme with this group, it adds it on. If I add this enzyme and take the group away, it'll turn it back into this. So we were able to take a synthetic mixture of D and L, treat it with an enzyme in a flask to react with one and not the other. Use some technique based on charge. Charge one interacts, charge one interacted, neutral one doesn't. Separate those two and then take that group back off and you get your enzyme. So this was for a long time, and actually still to this day is used by various companies, a way to purify. So we have this massive process that purifies this mixture over and over and over so we can churn out relatively pure enzymes, drugs, chemicals, whatever we need. Okay. The other cool thing they did, want to go all the way back to something mentioned in a previous podcast, where if you take your right and left hand together and try to fold them, like, you fold your hands together, you mesh your fingers, a right hand and a left hand fit together perfectly. Right hand and right hand, not so well, left hand, not so well, but RS. That's why racemic mixtures are typically denser and have higher melting points and boiling points than pure compounds because they literally are held together a little more tightly. So we exploit that. We take advantage of that technique by making a column that has something that interacts with this compound. So let's say we use another alcohol, something like attracts like, so I put a compound in there. If I make the compound some other compound that's R, the S will have a greater affinity and stick to it. The R will go through faster. So what I do is in this technique, I take these two, this mixture of R and S, put it into the column, and as it trickles down through the column, because the column has R, S is going to stick to it. Because it has R, the R is just going to meander through it, doesn't stick to itself. And so you end up getting R enantiomer coming off first, very quickly, and the other one comes off more slowly. This is a technique that we will be doing in OChem lab, where we use migration rates through environments. Sometimes it's a plate, sometimes a piece of paper, sometimes it's a column, to separate one species from another or identify how many species we have. It's a really, really common technique that we'll use over and over, but a lab technique for separating your S from your R. So R will come off first, S will come off later. So you can purify them that way. It's a little bit cheaper than an enzyme, a little bit cleaner as well. Cool, unadulterated bioexample. Again, you've matured and grown. You are no longer a general chem student. You're no longer in your first year of college. You're let go of all that immature high school perspective on things. And you, as a more mature learner of things, are saying, this is so cool. This is not a tangent. This is an application. So with your positive perspective, you're going to say, well, how do bacteria sneak into us without us recognizing them? So if you want to break into something, you want to sneak into something, you have two choices. Stealth, go in undetected, don't let the alarm system, the security system, don't let anything detect you and sneak your way in, option one. Or option two, who cares who sees you? Just wear such a thick coating of armor that nobody can get to you. Go in, do what you want, and leave. Bacteria are criminals. They are going to break into your cells or break into wherever they need to go to do the damage they want to do. So what they do is they go with the armor approach. They put on something we can't break down. So mention that we naturally make L amino acids. We are natural rel. So what the bacteria does on their cell wall is they use D-alanine instead of natural L-alanine. And so when they synthesize their cell wall, they take a glycine residue from one end and connect it to a D-alanine to the other end. And so they make a D network. So this whole thing is a little convoluted, but their polypeptidoglycan layer, this polymer system they have, has a sugar strand here. Connected to that sugar strand is cross-linking to what we have here. We have some of the amino acid, and then we have a whole bunch of glycines. And the new thing we make is right here. Not we, but they make that linkage right there. So they basically take all these fibers that if they didn't exist, so if I got rid of all that, then you can't see the line, but I'll do this. If you can see what I'm doing, I'm breaking the connection between the red and the blue. And so if we broke all those connections, then you would have this strand right here as one, this strand right here is another, this strand here is another, and so forth. So all these fibers, these linear fibers this way, are now all of a sudden connected. So now you have cross-linking. You have one side connected to another. Okay, so we do not have the ability to break that down. So let's say our body attacks this connection right here. Ta-da, we did it, except we didn't do it because guess what? This link is double fibered. It's connected there. Ah, dang it. Okay, well, let's break this link right, let's say right here. I'll get rid of that one. So I don't know if you can see me, but I'm doing right there. I got rid of it. Well, guess what? It's still connected here. It's still going across. So to break this thing down, it's going to be really tricky. Okay, so that protective armor, because it has a D-alanine right here, I don't have the enzymes to deal with it. So I can't break it down. It can exist however it does. So we get in this battle where I raise temperature in my body. I do whatever I can to try to make an unpleasant environment so it dies off. But if it's a strong bacteria, it will just grow at the same rate that it dies off and will propagate itself. So along came penicillin. Really simple observation if you think about it. Fungi, mold, bacteria, viruses, they all attack us. All these things exist to be parasitic, to destroy a host. I guess ideally, if they coexist with a host, they can live forever. But let's say they're all parasitic and destructive. Well, they're competing with one another. So somewhere along the line, somebody thought, hey, this mold is trying to do the same thing to this cheese that it seems like bacteria would want to do to it, but the mold is winning. So it ends up the mold had a compound known as penicillin. Penicillin happens to be the strain structure. It has a four-membered ring, highly reactive. It's basically a enzyme, a polypeptide, a whole bunch of amino acids stuck together with a very strained four-membered ring, which means it's ready to explode. It is highly reactive. It can react with anything, including the enzyme responsible for carrying out the formation of the cell wall. So if you do not let it make the cell wall, then, and rather than killing off bacteria, we're going to have, like, there's two types of antibiotics. One is bacteriocytic, that kills off your bacteria. It like knocks it down. So when bacteria are out of control, you knock them down, kill them off. But bacteriostatic basically doesn't kill it off. It just maintains the level by not allowing the growth rate to happen. So eliminate the formation of it, and then your body can naturally. So it prevents any growth input. So if your body starts killing off the bacteria little by little, it can't grow. So the uh, antibiotic you took, the penicillin-based antibiotic, prevents this linkage from ever being made in the first place. So it can't assemble its cell wall. The bacteria can't grow. Okay, lesson in bio in the middle of an OChem lecture, going all the way back to one of the cool little things of stereochemistry. That linkage right there, that D-alanine that we can't break down means we can't kill the bacteria, but with the help of our good friend mold, there's a compound we can use, an antibiotic, to prevent the formation of the cell wall so that you stop the growth of the bacteria and let your body gain control again by suppressing or killing off the existing bacteria. Hopefully these things are interesting to you. Transition from a mentality of tangent, extra stuff to cool application, career move, information that I will use to be a better person down the road. So just a little spiel on this. OChem, in my opinion, is the first class you come to that requires you to be a mature thinker and a mature student. And for the students who step up, and this is that first opportunity to do so, these cool applications, and how what I learned in one situation can apply in a new one. When you get excited, you've transitioned, you've matured in your academic approach. So we will no longer refer to these as tangents, we'll refer to these as applications. Applications are wonderful. That said, we are done with that application and done with this section. So the next Toddcast will transition yet into another topic. But have a wonderful, wonderful day. And thank you for being part of it. And I will see you at the next podcast. Bye.